Hello everyone, my name is Federico Nesti. I am from the Scuola Superiore Sant'Anna of Pisa, and I will be presenting our paper evaluating the robustness of semantic segmentation for autonomous driving against real-world adversarial patch attacks. It is already known that it's possible to fool image classification and object detection models with real-world patches. Semantic segmentation plays a role in obstacle detection pipelines for autonomous driving cars. The autonomous driving scenario includes some possible attackable surfaces, on which we can attach adversarial patches, like in this case. So the question is, are semantic segmentation models prone to real-world patch attacks? This paper presents an extensive evaluation of the robustness of real-time semantic segmentation models. It also proposes a novel loss function to improve the attacker's capabilities. We are using the Carla simulator to provide fully controllable autonomous driving environments. In this way, we are able to test realistic attack scenarios. We finally show the first real-world patch attack against semantic segmentation models. To evaluate the robustness of these models, it is necessary to generate some adversarial patch datasets. This pipeline is used to craft the patches using Cityscapes or the Carla-generated datasets. The patch appearance is randomized to simulate real-world lighting effects, and the patch placement within the image can follow two different rules. In the standard expectation over transformation case, it is randomized. In case we are using Carla-generated images, we also collect camera to attackable surface transformations that allow for accurate patch placement. This strategy is novel and named scene-specific attack. It outperforms the expectation over transformation-based attack. Once the patch is placed, the patched image is used to predict the semantic segmentation output. Then, the loss function is computed and used to backpropagate into the patch. We also propose a novel loss function that is based on the definition of the set upsilon. This subset of the image pixels specifies all the pixels outside the patch that are correctly classified. According to this definition, we divide the standard cross-entropy loss in two terms, and we weigh these two terms with a parameter gamma. High gamma values, close to 1, help the optimization process to misclassify pixels that are not yet misclassified. As shown in these graphs, both for Cityscapes and Carla-generated datasets, our loss formulation outperforms the standard cross-entropy loss for any value of gamma tested, both in terms of convergence rate and attack performance. These are the results on the Cityscapes dataset. Although the effect is visible, there are some networks that are much more robust than others, as shown in this table. In particular, we found that PSPNet and BiCnet are the most prone to patch attacks, while DDRNet and ICNet are more robust. Here we present the effect of the scene-specific attack. From this video, it is clear that it outperforms the standard expectation over transformation formulation. However, the attacks are not that effective, and in general, we can see from tabular results how these networks are not completely fooled by these attacks. These images show the patches that we printed to carry the first real-world patch attack against semantic segmentation model. Top image shows the almost null effect that a random patch has, whereas the bottom image shows the adversarial effect. The effect is visibly limited to areas close to the patch. The spatial robustness properties of these semantic segmentation models is really interesting and is worth further study. To conclude, even though some patches are able to influence the performance of some real-time semantic segmentation models, it is clear that their effect is limited, especially when considering the spatial distribution of the adversarial effect. This is an interesting line of research that we are already exploring with further experiments, defense methods, and formal discussions on the spatial robustness of these models, which looks promising. Thank you for your attention.